Over to you, Rudi.
Awesome. So hi everyone. As mentioned, my name is Rudi Finzgar. I am a PhD student at the Technical University of Munich and with the BMW group. And today I will present our preprint on designing quantum annealing schedules using Bayesian optimization. So I'll start with a bit of motivation. I think this paper in the top left corner of your screen, it's probably my favorite paper from 2022. And for those of you who aren't familiar with this really nice work, I'll give a 30-second summary for now. So it is from the QERA / Grukin / Vuletic labs at MIT and Harvard. And the whole kind of idea of the paper is to use closed-loop optimization to perform or to optimize adiabatic protocols on neutral atom quantum computers to solve the maximum independent set problem. And I found it because it kind of came amid this backdrop of somewhat pessimistic results in quantum optimization. And in this paper, they show that you can hope for speedups. And not only that you can hope for speedups, they even show this in practice. On an experimental device, and as the device that came out of this QERA computing company, which is affiliated with some of the people that are co-authored the original publication. Me being an OZ PhD student, I was eager to try it out on Amazon Bracket as soon as it became available. So I set up some graph instances. I said, oh, let's optimize the schedules. So I dug deeper into the supplementary material of the original publication, and I found that you require, or that you need, roughly 100,000 calls to the quantum computer to optimize the protocols for a single graph instance. And not having not been a great expert in neutral atom quantum computing at the time, I thought to myself, all right, sure. So I got around to actually implementing these things. And what I found in practice is that I was able to do roughly, obtain roughly 10,000 shots or 10,000 measurements from the quantum device through Amazon Bracket. So the question that I asked myself was, how can I do this more efficiently? I cannot, wait for 10 weeks to optimize adiabatic protocols for a single graph, as this won't allow me to write any papers and finish my PhD anytime soon. And this is how I got to Bayesian optimization. So to give you, let's say, a short overview or a brief overview of our approach, what we do is we use or we parameterize quantum annealing or quantum adiabatic paths using a variety of different parameterizations. And all that these parameterizations have in common is that they share some, or they have some set of parameters which you can use and which uniquely define them. And then we have some way of evaluating these schedules. So we put them onto the quantum device, or we evaluate them in numerical simulations, and then this produces some sort of a figure of merit, which basically tells us about the quality of such a schedule. And then we use Bayesian optimization to predict the next set of, or to propose the next set of parameters to evaluate, and as such, we have this closed loop type structure. To give you a concrete example, we could do this, for example, for vanilla quantum annealing, where we have a single control function, which interpolates from this initial mixer Hamiltonian to a target Hamiltonian. And then there is a variety of ways of how to get from u of t equals 0 to u of t equals to 1. And this is kind of specified by these quantum annealing schedules. Right. To give you a short outline of the talk, I'll start with a brief and gentle introduction to Bayesian optimization before going on to the results. These results are have been carried out or are results of experiments carried out on two paradigmatic model systems. One of them is the piston model, which was mostly used for numerical simulations, or of which we mostly perform numerical simulations. And then I have some numerical simulations and actual experimental data on neutral atom quantum computers to solve the maximum independent set problem. Right. So let's get right into it. Let's start with a brief intro to Bayesian optimization. So Bayesian optimization is an optimization method which is designed specifically to optimize functions that are difficult to evaluate. So with difficult to evaluate, I mean, this can be expensive, this can take a long time. So basically, you are in a setup where you would like to evaluate your function as infrequently as possible. And you also assume that you have, no information about or little information about the inner workings of the function. So you can treat it in this sort of black box setting. So in this, illustrative example, let's say we have a function f of theta, where f is our figure of merit, and let's say that this is our ground truth, which is, of course, unknown to us. And the theta, could be, for example, the parameters of our annealing schedules, and this could be, for example, the ground state fidelity of our annealing protocol. So what we do, or what we can always do, right? Even if it is expensive, we can always evaluate f at a certain, set of points or set of parameters, theta ops here. And now the question is how to find the maximum using as few evaluations of this function as possible. So what is done in Bayesian optimization is that you use Gaussian processes as a model for the objective function. So basically, you don't know anything about a function, but you impose some sort of model which has parameters on top of it, and then you try to fit that model to the observations as they come in. And this is done basically by, in the language of Gaussian processes, this is done by conditioning the probability distribution, because Gaussian processes are, in some sense, basically probability distributions over functions, by conditioning this probability distribution over functions on the observations that one has made of the figure of merit. So, this is really just standard probability in terms of, just looking to this from this Bayesian perspective. And then we use this model that we have built of our function in something that is called an acquisition function, which is basically, some heuristic that, determines what is the next point that we should try out. And one, nice example of a heuristic is, for example, to take some linear combination of the mean value of our model and the standard deviation, right? So in this sense, we kind of balance exploitation and exploration, right? The exploitation coming from high mean values, meaning, this will probably be a good point to sample, and then high standard deviation, meaning, well, we don't really know that much about this part of the parameter space. It might make sense to evaluate a few points from here. And then, you can progressively, you can, play around with these things so as to get a nicely working configuration. I maybe at this point, it's nice to mention that, this has been used and is being used extensively in machine learning, for example, for hyperparameter optimization, right? Where each function evaluation, quote unquote, corresponds to training a whole neural network, for example, which is, obviously a very time-consuming task, which you would like to do as few times as possible. A couple of bonus points about Bayesian optimization is, one is it being this probabilistic / Bayesian approach, it has an inherent ability to handle shot noise, meaning that or noisy observations in general. So meaning that if the points that you are observing are subject to, for example, experimental noise, shot noise, or something like that, you can really naturally incorporate this into your model. And another nice thing is that you don't need any gradients of f. As I've mentioned at the beginning, it is let's assume this black box set. All right. So let's try to visualize how this works. So say we have a couple of observations that we have made here, made in black. And then the Bayesian optimization suggests that we next sample this, red point theta next. So how does, basically, how does the optimization proceed? We evaluate this point, right? And we update the model. Bayesian optimization produces a new point to sample. We evaluate it, we update the model, and then, in this, of course, cherry-picked example, we pretty quickly find a point that is relatively close to the global optimum. And this is kind of, I would say, an illustration of how Bayesian optimization will work in practice. Of course, in a real setting, right, parameters will be higher dimensional. The landscape will be more rugged, but I think this gives a nice idea of how this works. All right. So let's talk a bit about the results. So what can one do with this relatively powerful tool? Right, to remind you, so this is our setup. We have schedules that take in parameters. We evaluate them in hardware or numerical simulations, and then we optimize the parameters of these schedules using Bayesian optimization. And first, I want to talk about our results on a what's called a traditionally well-studied spin system, which called the P-spin model. So the P-spin model comprises p-body, all-to-all p-body terms, so sigma z terms. And even though it's a very symmetric, or because it's a very symmetric Hamiltonian, one can restrict the simulation of annealing protocols to a very small, I think, linear or quadratic number of in n number of states in the Hilbert space, meaning that one has access to scales which you wouldn't have otherwise in considering just general quantum Hamiltonians. And another very nice feature of the P-spin model is that if you take this canonical annealing path starting from a sigma x mixture Hamiltonian to this target Hamiltonian, the system exhibits a first order phase transition. And as many of you might know, typically such first order phase transitions are associated with an exponentially long adiabatic time scale, meaning that the gap along this path vanishes exponentially, such that you will need to have an exponentially long annealing time in order to prepare the ground state of this model or of this system. So here we test then several different parametrizations of this U function, which controls how we go from the transverse field Hamiltonian to the target Hamiltonian, and we optimize the schedules using Bayesian optimization. And first of all, if you look at the naive linear path, right, which would basically just correspond to a straight line from 0 to 1, going from 0 to time final, you get this really nice or really bad exponential decay in the target fidelity. However, using different parametrizations of the schedules, you get varying improvements as you optimize the schedules using Bayesian optimization. Another nice thing is, I mean, and this is maybe, I would say, a relatively important point when one considers Bayesian optimization for this use case is, of course, the fact that Bayesian optimization does not fully exploit or does not use any gradients and stuff like that means that it has certain features when it comes to its efficiency and when it is best deployed. So of course, if you have access to millions of executions, right, there will be methods which will converge better in the long run. But to have in this intermediate, let's say, frame of the number of iterations or number of evaluations that one has at one's disposal, it makes a lot of sense to use Bayesian optimization compared to, for example, standard optimizers such as SPSA, which might converge better at the end, but might take a longer time to get to that particular result or to that particular point. Right. Another nice a nice feature about the piston model, I think from a more, let's say, theoretical perspective, is that this first order phase transition that I mentioned before can be avoided if one starts from an approximation of the ground state. So the ground state of the piston model, if we look at it again here, is I think it's not that difficult to see it. It is all spins pointing up, right? So that you have all -1 contributions. That is, of course, for odd p. I should mention. So yeah, this is another small detail that I failed to mention so far. So all of these results are for p equals 3, but they generalize to other odd values of p quite well. So exactly. So as I said, for odd p, the ground state is all spins pointing up, and one can avoid the first order phase transition if we begin the annealing in a state which is an approximation of this final ground state. And you can come up with different approximations of this ground state, but one that was proposed in the literature by Yamashiro et al. Was to consider product states of this form, where a fraction of p of spins pointing in the correct direction, and the remaining spins are pointing in the opposite direction. And what you then do is you come up with this reverse annealing Hamiltonian, which has 2 control functions instead of 1, and which basically begins in this H init, which is a Hamiltonian that has this initial state as its ground state, before turning on this transverse field Hamiltonian, which is typically seen in quantum annealing protocols, and then kind of ramping up this target Hamiltonian. So basically, you have a linear or a quadratic decrease in H initial, a increase and then a decrease in the transverse field Hamiltonian, and a steady increase in the target Hamiltonian. And what has been shown is that if you fine-tune this parameter gamma, which controls the strength of the transverse field, one can avoid the first order phase transition along this adiabatic path. However, this is nicely visualized here in the thermodynamic limit. So for n equals to infinity, you see that with increasing qualities of the initial approximation, the line of the first order phase transition gets smaller and smaller and smaller, right? And then as you see that your initial approximation ratio exceeds 0.9, the linear path going from 0, 0, so from the start of this protocol, to 1, 1, which corresponds to the end of the protocol, where the Hamiltonian equals target Hamiltonian, avoids this first order phase transition. So, long story short, if you fine tune the parameters such that this phase diagram looks the way you want it to look, you can get an exponential speed up because you can avoid the first order phase transition, which leads to this exponentially closing gap. However, I've been mentioning the word fine tuning quite a lot. You can, if you slightly change gamma, for example, gamma equals 5, no matter how good your initial approximation ratio is to reasonable bounds, you always hit this line of first order phase transition, so there is no such exponential speed up. And this you can see nicely in the diagram, which plots the minimum spectral gap along these paths. So you see that for gamma equals to 5, you still have an exponential decrease in delta, whereas for gamma equals to 2, this is almost constant. So the question is, can one, because this typically, this is a very nice system, so you have access to such a phase diagram, but should this be transferable over to real world optimization problems? This typically won't be possible, right? You won't be able to compute the whole phase diagram. You won't be able to, do this thermodynamic analysis where the first order phase transition occurred and so on. So ideally, you would have, some robust protocol which would be able to circumvent this need for fine tuning. And I think I spoiled it enough that you will guess that I do this using Bayesian optimization, where I basically parameterize these functions s of t and lambda of t by a set of parameters, and then I optimize the path using a Bayesian optimizer. And you see that even for so of course this is now a finite system size version of this plot here, and you see that there is this region of a decreased gap shaded in darker colors here that kind of mimics this shape for the thermodynamic limit here. And what is nice is that these Bayesian optimized paths kind of find this opening in the first order phase transition, or the region where the first order phase transition happens in the thermodynamic limit. And this is then manifested in higher fidelities, both compared to quantum annealing, right, which also, of course, suffers from this first order phase transition, as well as compared to non-optimized reverse annealing. And yeah, is there anything else? So the last thing I want to talk about, or the last result section that I want to talk about, is the kind of going back to the original motivation and the paper from the Q-era folks on optimizing the maximum independent set on Q-era neutral atom quantum computers. So to give you a bit of background, the maximum independent set problem is a very famous combinatorial optimization problem that deals with graphs. In particular, given a graph, you're tasked to find the largest subset of vertices which are not connected by an edge. And although that is trivial to state, the optimization problem itself is NP-hard, meaning that in the worst case, algorithms are expected to have exponential complexity. A particular family of graphs called unit disk graphs were shown to be naturally mappable to neutral atom quantum computers. And you see an example of a unit disk graph in your top right corner. So unit disk graphs are formed by basically positioning points on a 2D plane, and then connecting points which lie within a certain radius of each other, right? So basically, it's kind of built off of this geometric structure that, if a point falls into a circle with a given radius, in this case, a unit radius, then these 2 points are connected by an edge. And for those of you familiar with neutral atom quantum computers, I think, or with Rydberg physics in general, this will, kind of immediately flash a light in connection with the so-called Rydberg blockade. So in neutral atom quantum computers, you have these atoms, positioned in optical traps, and they are, shined onto by lasers. And these lasers excite the atoms into very highly excited states called the Rydberg states. And one very interesting property of Rydberg atoms, and in particular the interaction between Rydberg atoms, is that if you have two such atoms in close proximity to each other, only one of them will be able to go into this highly excited state at the same time. And this, kind of naturally maps to the Rydberg, to the maximum independent set on unit disk graphs, where you also have this independence constraint that no two atoms that are connected by an edge, or that are in spatial proximity to each other, in this case, can be simultaneously excited or simultaneously put into the independent set. As such, kind of the ground state of this Hamiltonian on a neutral atom quantum computer directly corresponds to the solution of the maximum independent set problem. So how does one prepare such a ground state? One option is to, of course, use adiabatic protocols. So maybe skipping over this a bit. The most important parameter is the tuning parameter delta, which basically favors or kind of determines whether you favor excitations or non-excitations of individual atoms, which is captured by this number operator, which is 1 if the atom is excited and 0 otherwise. So you can see that, for positive values of delta, you would like to have as many of these n's in the 1 state as possible, which is kind of in conjunction with the fact that you want to have as many atoms in or as many vertices in the independent set as possible. So that a typical adiabatic protocol will start with a negative value of delta, and then ramp up to a positive value of delta, and kind of the path which is taken, we here optimize using Bayesian optimization. So first, to kind of go back to the original comparison with the Q-era paper. Using Bayesian optimization, we can optimize these schedules using roughly 20 times less shots than the original paper, which is nice if you actually want to carry out some experiments yourself. And we first try to do this for a collection of very small atoms, which are accessible in numerical simulations as well. So we take such small unit disk graphs and we compare different ways of optimizing, or different parameterizations of the tuning path. And you see that for this finally chosen parameterization, we get a very nice independent sets compared to these very noisy or all over the place heat maps that we see here for the linear case or the unoptimized case. And this is kind of in nice agreement with the bar plot below. So in the bar plot below, I plot the probability of observing or of seeing the maximum independent set for each graph across various repetitions or some repetitions. So basically, what is done is we optimize the protocols in classical simulations of the system, and then we transfer the optimized parameter directly to the device where we evaluated them. And what is very refreshing to see is that the numerical simulations and the result from the quantum computer here in the darker shades are in very nice agreement for all of the graphs, which speaks volumes about the relatively low error rates that the device apparently possesses. Of course, the nice thing about the Q-era device is that it is a a relatively big device. I think you can load up to 250 atoms into it. So of course, I also want to try out graphs which are beyond classical simulability, meaning that the whole end-to-end optimization was performed on the actual device. So basically, there was this hybrid job setup where I basically send the job to the quantum device. I get a result. I propose a new set of parameters, and this was really implemented in practice for a collection of four such large graph instances. And the nice thing is in the bottom, in the histograms in the bottom, where you see the energies that one obtains from the device. First, for a linear protocol, which has not been optimized, and then once the protocol has been optimized, you see there's a substantial shift in the quality of the result that one obtains. Unfortunately, the let's say relatively low availability of the device precluded any systematic experiments on these large graphs, which I hope to be still able to do in the future. So even though Bayesian optimization is, I claim, very efficient, it's still not efficient enough for very systematic studies of such large instances on the real device. All right. So this is basically it. Let me maybe conclude with a few take-home messages. I'm of the opinion that Bayesian optimization is a very promising tool for such near-term, NIST-key quantum optimization approaches, because I get the feeling that this pairing of analog devices, which make larger system sizes accessible, and as it seems they have very low error rates, are kind of very nice pairing. So you have this access to large system sizes on the one hand, and relative resource efficiency on the other hand, especially compared to other approaches such as QAOA, where you need to increase depth, and with that also the number of parameters that need to be optimized and so on. And also I think the results that we show are promising in the sense that we deploy them both in numerical simulations where we have access to large system sizes, as well as in actual experimental settings where we get these really nice improvements using Bayesian optimization. Of course, I couldn't tell you everything that is in the paper. There's results on noisy simulations. There's all sorts of things. So feel free to check out our preprint. In the end, I would of course like to thank my co-authors, Martin, Kyle, and Helmut from AWS or Amazon, and Hidetoshi from the Tokyo Institute of Technology, and of course thank all of you for having me here and for your attention. So feel free to ask any questions you might have.
Yes, thank you very much, Rudi. Very interesting talk, lots of interesting things. A round of applause from me on behalf of the whole audience. And as Rudi says, let's open this up for questions. If anybody has questions, either raise your hand or just unmute and shout out.
Yeah, I have a question. Can you hear me?
I can hear you.
Good.
Go ahead.
So essentially, schedule optimizations are usually done for a family of problems. So then when you get a new problem from that family, you don't need to do the whole optimization again. You can just use the schedule that you found. Do you make a claim that the schedules that you found will work for a new problem that you have not seen before from this family?
I am not making that claim, although I think this could very well be the case. I think, for example, for maximum independence set problems in this neutral atom context, there has been quite a lot of analysis done that, for example, the minimum spectral gap typically occurs at the end of the protocol, meaning that there is some sort of a generic behavior that one sees. And I think, first of all, maybe even just reusing a schedule that one has done for another graph instance could be interesting. But I think more than that, kind of tailoring your ansatz towards some pre-known, let's say, gap profile, such that it makes it easier for Bayesian optimization, or for any optimizer for that matter, to learn.
Thanks. So when you said that you need 20 times less shots, how did you quantify that exactly?
I counted the shots in the sense that I have. It is difficult, of course, to compare, right? The device that they used, in their experiments, of course, was also a different device than the one I used. So it's not a apples and apples comparison, maybe more of an apples and pears comparison. But I can count, the number of shots that I need to optimize my schedules using Bayesian optimization to get good results. And they reported the number of shots that they needed in their experiment.
So what do you mean by good results? Do you have a stopping criterion of some point, some form?
No, I do not have a stopping criterion. So in this case, I use the same. So I wanted to have as little of this hyperparameter tuning as possible in my paper. So what I have is basically a predefined but motivated setup for Bayesian optimization, which I then deploy for various use cases. So that's one nice thing about Bayesian optimization, is that it is relatively robust. Even though you have a lot of hyperparameters, it typically works well already out of the box. So it's in that sense, I can very much recommend it.
Okay, I see that. Kathy,
Thanks.
go ahead, Kathy.
Yeah. Thanks. That was a great talk. Really, really interesting. And actually, when I raised my hand, I had the question that was just answered. So thank you for that. But I did have another, I guess, a question about the quantum annealing results and the simulator that you used, a simulator to get your in your first examples, the optimal schedules, right? Did the simulator have noise? Is there a noise model in that simulator, or is this sort of assuming a noise-free perfect system?
So yeah, as I said, the results that I showed are noise-free. But I did also consider dephasing noise. So in this whole, let's say, reverse annealing, let's say, landscape, there was a couple of works from a couple of years back where people showed that if one adds dephasing noise, or any noise for that matter, one might lose the speed up which one gets from starting from a better initial point. I think I might even have some slides on that in the backup. Exactly, so this you can see here in the right block. But what I see, or what I noticed, of course, it's more difficult to simulate these things than if you have noise, right? Because you lose this. You're not. You have to go into density matrices. You have to simulate a master equation, and so on. So you're limited to smaller system sizes. But I am still able to recover at least some of the speed up, even in the presence of noise, if one optimizes the schedules using Bayesian optimization. But more on that in the paper.
Yeah. Okay. Well, thank you. I guess my other question is there some objection to trying this out on a physical quantum annealing system? Is there some obstacle to doing that?
No.
Do you plan to?
Not at the moment, but it would of course be interesting. Yes.
Yeah. Okay. I guess I actually have a question for the theoreticians in the room. I'm not a theoretician, and so as far as I know, dephasing is not one of the tall poles in quantum annealing computations. It's a problem in gate model, but is that the case? Am I just kind of behind the times with that in that respect? I don't know.
It
that
depends
necessarily-
on the system, but I think in D-Wave dephasing was the strongest, and in this atoms, I don't know.
Uh-huh. Okay, I was just curious. All right, thank you.
I had a question about the technology of the Quira system. You said that you could get around 10 or maybe 40,000 shots per week through
Yes.
Is that per user, or is that the entire, if you have complete control of the machine for a week? What's actually taking the time here?
So the story was that as this device became available on Amazon, they first made their availability only for 10 hours a week. So basically, it was only 10 hours a week where all of the users in the world had access to this device. So first of all, there's the queuing times, of course. But more than that, I mean, also the whole, like, let's say, neutral atom technology is relatively slow in some sense. I think a good, let's say, back of the envelope type of estimate is that you need roughly 0.6 or something like that seconds per shot. So this, even if you have the whole 10 hours to your disposal, it still takes a long time. And I think they even report some very interesting numbers in the supplementary material of this paper, which I don't know off the top of my head, but they were surprisingly long to optimize even a single graph.
And maybe this is not your area of expertise, but that's mainly the initialization of the array or the readout. Well, what's actually taking the time? Do you know?
I think partially it's probably the initialization. I think one of the bigger bottlenecks, at least at the beginning of these neutral atom platforms, was the loading of the atoms. And then, but I'm by no means an experimental expert on such matters. So I'm not, in the interest of not saying anything wrong, I'll better shut up.
Correct answer. Good. Any other questions for Rudi from anyone in the audience? Well, if not, let's thank Rudi once more. Thank you very much, Rudi. Very interesting talk. And I look forward to seeing people at the